In Chapter 8, we're introduced to the idea of a confidence interval. A confidence interval is a way of estimating an unknown parameter. Before we get to the definition of a confidence interval, let's talk a little bit about the type of estimates we've already been doing in this class. A point estimate is a single number used to estimate the value of an unknown quantity. When you use one number to make a guess at some unknown value, that's what we call a point estimate. So for example, if you were to guess that it was around 50 degrees outside, you're using one number, 50, and a unit, degrees, in order to guess at this unknown quantity, which is the air temperature. But we've actually done some nerdy point estimates in our class using statistics. A statistic is used to estimate a parameter, and we've seen a couple of these. The sample mean, x bar, is a point estimate for the population mean, mu. The sample mean is a point estimate because it's a single number. We take all of the data in the sample, we add it all together, we divide by the number of values, and it gives us a single number. And we use that single number to estimate the population mean. So that's an example of a point estimate because it's one number used to estimate this unknown population mean. Similarly, the sample standard deviation, S, is a point estimate for the population standard deviation, sigma. Same idea. We take all of the sample data, we do some calculation to get the sample standard deviation, and we use that as an estimate for the population standard deviation. It's a single number used to estimate this unknown quantity. But there's nothing restricting us to using a single number to estimate a quantity. Instead, you might want to use a range of numbers, and that's what we call an interval estimate. An interval estimate is a range of numbers used to estimate the value of an unknown quantity. So instead of using a single number to make your guess, you might use a range of numbers, an interval. Instead of saying you think it's about 50 degrees outside, which would be a point estimate, you might say that it's between 45 and 55 degrees outside. And now you've got what we call an interval estimate. Now, we haven't seen any examples of interval estimates in our class, but that's exactly what a confidence interval is. A confidence interval is an interval estimate with a special quality. A confidence interval is an interval estimate with a specified confidence level. Now, confidence level is a very technical term, and we're going to define it specifically later. For now, just think of confidence level the way that it sounds. A confidence level is basically how sure you are that your estimate is correct. And that confidence level is what makes a confidence interval special, because you can say how sure you are that you're right. The issue with a point estimate is that we can't really be sure how good our estimate is. But with a confidence interval, we know exactly how sure we are that we're right because there's a specified confidence level. We can say that we're 95% sure that we're right or 99% sure that we're right. And that begs the question, how could you possibly know that? It all falls back on our understanding of probability distributions. In particular, if we know that the data is normally distributed, then we can apply the properties of a normal distribution to help us find this confidence interval and say how sure that we're right. And to demonstrate how that works, I'm going to introduce you to the empirical rule, or at least part of it. And I've written down the two parts of it that we would be interested in for this discussion. It says in any normal distribution, approximately 95% of the data is within 2 standard deviations of the mean, and approximately 99.7% of the data is within 3 standard deviations of the mean. Well, let me quickly describe what this says using pictures. If you've got a normal distribution with mean, mu, and standard deviation, sigma, and you add 2 standard deviations to the mean, and you also subtract 2 standard deviations from the mean, you get these two bounds, mu minus 2 sigma and mu plus 2 sigma. Those two bounds are 2 standard deviations away from the mean. If we were to look at the area contained between those two bounds, the empirical rule says that that's around 95% of the data. So the area encapsulated here would be around 0.95. Similarly, if we were to add 3 standard deviations to the mean and also subtract 3 standard deviations from the mean and find the area encapsulated within that region, that would be around 99.7% of the data, according to the empirical rule. And we take advantage of this to construct a confidence interval. Because we know that 95% of the data is within 2 standard deviations of the mean, and because we know approximately 99.7% of the data is within 3 standard deviations of the mean, we have the ability to assign a level of confidence to specific estimates. If we want a certain level of confidence, we just have to go a certain number of standard deviations away. The sample means are going to be normally distributed in a lot of cases. If you know the population is normal, then the sample means are normally distributed. If you choose a large enough sample size, the sample means are normally distributed by the central limit theorem. So suppose we've got a set of normally distributed sample means. The quantity we want to estimate is mu, but that's in the middle of the distribution. Even though I don't know what that number is, I know it's got to be in the middle. The standard deviation of the sample means is the standard deviation of the population divided by the square root of the sample size. So if we know what sigma is, we can calculate this quantity as well. And here's the beautiful thing. Even though we don't know what mu is, we know that 95% of all of the possible sample means fall within 2 standard deviations of that. 95% of all possible x bars live in this interval. So if we were to calculate one x bar at random by gathering a sample and getting that sample mean, we know there's a 95% chance that the x bar is in there. Reversing that logic, if we start with x bar and we create an interval by going 2 standard deviations away from it in each direction, and we get this interval of values, we can be 95% sure that the value of mu lives somewhere in that interval. Why? Because there's a 95% chance that we started within 2 standard deviations of the mean. Let me show you how this would work in a specific example. A random sample of 36 fun-sized bags of M&Ms yields a mean count of 32.5 pieces of candy per bag. If we assume to know that the population standard deviation is 3 pieces, construct a 95% confidence interval for the mean number of M&Ms in all fun-sized bags. Before we get to the actual example, I want to talk about exactly what we're doing here because it's powerful. We're taking a very small sample, only 36 bags, and using that small sample, we're going to come up with an estimate for the mean number of M&Ms in all fun-sized bags. And not only are we doing that with such a small sample size, but we're going to be 95% sure that our estimate is right. It is very, very likely that our estimate will contain the true mean. Now, how can we do that? Well, our sample size was 36, which is large enough to invoke the central limit theorem. So we know the distribution of these sample means will be normal. In the middle of this distribution is the very number that we're trying to estimate. Remember that we don't know what this is. But what we do know is if we go 2 standard deviations away from that in each direction, if this is 2 standard deviations to the left, and this is 2 standard deviations to the right, then 95% of all possible sample means fall within that range. Well, we have a sample mean to work with. Somebody analyzed the data and found a mean count of 32.5 pieces of candy per bag. Now, we have no idea where that 32.5 falls in this distribution. There's a 95% chance it falls inside here. It could fall on one of the tails. We don't know where it is. But the logic is there's a 95% chance that 32.5 lives within this range. That also means that we can be 95% sure that an interval centered about that will contain the true population mean. We just have to know what the standard deviation is, but we have the information for that too. We were assuming we know the population standard deviation is 3 and the sample size is 36. So our standard deviation is 3 divided by the square root of 36, which is 3 divided by 6, or 1/2. So if we go 2 standard deviations away from the sample mean in both directions, we get an interval estimate. So our sample mean was 32.5, our standard deviation was 1/2, and in order to be 95% confident, we go 2 standard deviations away from the mean. So I do 32.5 minus 2 standard deviations, which is 31.5, and we do 32.5 plus 2 standard deviations, which is 33.5. So what did we just discover? Well, we can say that we are 95% confident that the mean number of M&Ms in all fun-sized bags is between our 2 bounds of 31.5 and 33.5. We got that because that was 2 standard deviations away from the mean in each direction. Again, let me explain the logic here. We're 95% sure that our sample mean will fall in this range, because 95% of all sample means fall within 2 standard deviations of this unknown mu. Therefore, if we go 2 standard deviations away from our x bar, we can be 95% sure that mu falls between these two bounds, and that's what we write. We are 95% confident that the mean number of M&Ms in all fun-size bags is somewhere between 31.5 and 33.5. We've come up with an interval estimate for the mean number of M&Ms in all fun-size bags, using just a sample of 36, and we're 95% sure that it's right. Now, that estimate did hinge on us assuming to know the population standard deviation, and you could criticize that part of our analysis, but we're going to learn how to get around that too, without having to make that jump of knowing the population standard deviation. Now, if you got a little bit lost in the arithmetic here, let me tell you that we're going to eventually rely on the calculator to do all of that number crunching for us. If you're lost in the logic of how it works, that's understandable, but let me try to explain it one more time. When we gather a sample mean, we're 95% sure it's within 2 standard deviations of the thing we're trying to estimate. So what we did was we took our sample mean, which was gathered from real data, and then we went 2 standard deviations away from it. If we're 95% sure that x bar is within 2 standard deviations of mu, then the interval that's 2 standard deviations away from our x bar is 95% likely to contain mu. That's the logic. What if you wanted to be more confident? Same example, but now let's construct a 99.7% confidence interval. Well, how do we get more confidence? How do we capture more x bars? Well, we go further away from the mean. According to the empirical rule, if you want to enclose 99.7% of the data, you just go 3 standard deviations away from the mean instead of 2. It's the same scenario where we've got these sample means for samples of size 36. We've got this unknown value mu in the middle. Mu x bar is always equal to mu. And the standard deviation of the sample means is the standard deviation of the population divided by the square root of the sample size, which still reduces to 1/2. But now we want to encapsulate 99.7% of all possible means, so we go 3 standard deviations instead of 2. Well, we know x bar is 32.5, and we know sigma sub x bar is 1/2. So we go 3 standard deviations instead of 2 standard deviations away from the mean. So I do 32.5 minus 3 1/2. Well, that's 32.5 minus 1.5, which is 31. And then we do 32.5 plus 3 standard deviations. So that would be 32.5 plus 1.5, which is 34. And now we've got these bounds for our new confidence interval, and we're more sure that this one's right. We are 99.7% confident that the mean number of M&Ms in all fun-size bags is between 31 and 34. We're very, very sure that the mean is within this range. 99.7% confident. And why can we do that? Well, 99.7% of all possible sample means are within 3 standard deviations of our unknown quantity. So if we take our sample mean and we go 3 standard deviations away from it, we can be 99.7% sure that mu falls somewhere in that range. Notice that our interval got wider. When we were 95% confident, we went from 31.5 to 33.5. When we went for more accuracy and up this to 99.7%, we lost some precision. Our interval got wider. There's this balance between how sure you are that you're right and how wide your interval is. And this answers one question that I get asked quite a bit. Well, if we can say how sure we are that we're right, why not go for 100% confidence? Like, what's stopping us from going there? Well, in order to get 100% of all possible sample means, you'd have to go all the way to the left and all the way to the right. In order to get 100% of the area, you can't stop anywhere. You have to go forever. So we could say we are 100% confident that the mean is between negative infinity and infinity. That's not a very useful statement. That's just saying we're 100% sure that the mean is a number, which is true but completely useless. There's this balance between accuracy and precision. You want to be accurate, you want to have a high level of confidence, but you can't make your level of confidence too big because then your interval is so wide that it's useless. We'll discuss that in future sections. And again, I want to alleviate any concerns that you have. While this arithmetic isn't hard, that's because we're using the empirical rule. If we didn't want 95 or 99.7% confidence, then the math gets a lot harder, and because of that, we're just going to let the calculator do all of the number crunching. We're going to focus on how to do these interpretations. We do have to be able to use the calculator. There's a learning curve there. It's not going to be trivial because we're going to be looking at 3 different scenarios. We're going to be looking at examples like this one where we're estimating a population mean when the population standard deviation is known. Then we're going to move on to the more realistic scenario where you're estimating a population mean but you don't know the population standard deviation. And we also want to talk about estimating a population proportion. So while we will be using the calculator to do the number crunching, we're going to have to figure out which scenario we're in because there's a different calculator function for each. But once we've done that, that'll spare us having to do all of this stuff, where we're doing all of the arithmetic by hand, and we'll be able to focus on our interpretations. Okay, so I hope you have a feel for what a confidence interval is. It's an estimate for a parameter where we can gauge how sure we are that that estimate's right, and that's the power that it has. And I don't want you to miss out on the fact that we're doing this estimate for the entire population, using a very small sample size in some instances. In this example, we used a sample of only 36 to come up with an estimate for all bags of M&Ms of that Halloween size, that fun size. I know this video was rather abstract and it went kind of fast. We're going to slow this down as we go section by section through the chapter, focusing on each of these 3 scenarios. We're going to break this down scenario by scenario, and that we'll be using the calculator to speed this up a little bit so that our focus can be on the interpretations and how this works. If you have any questions or concerns, don't be afraid to contact me.